In this video, I'm going to talk to you a little bit about statistics with respect to distribution of data. Now, what I'm talking about is when we take univariate data, that means just one variable data, and look at it as it's laid out, as it's displayed, as it's distributed. There are three main ways to show data in a visual format. The first way is a histogram. A histogram is just bars without spaces. It's important to keep in mind without spaces. That's what makes it a histogram, that show an interval or range of values. Now that's kind of confusing for some students. What I mean is if this beginning of the histogram starts at 0, then this bar has to land at a number, let's say 3 units away. I'm just showing you as an example. The next bar needs to be another 3 units away. The next bar, another 3 units, and so forth. So that means that the range of the first bar of data goes from 0 to 3. The second bar represents all the data values that go from 3 to 6, then from 6 to 9, and so forth. That's what a histogram looks like. A box and whisker plot, or a box plot, is a display of a box and whiskers, that's how we talk about it, that shows box and whiskers that show data split into fourths, groups of 4. For example, if we have a data set that's got, 20 items in it, 20 values in it, then you're going to have 4 items in this group right here in this whisker. You'll have 20, let's use numbers so we can do it this way. If I've got 20 values in my data set, 20 divided by 4 is 5. That means I'll have 5 values in this space here. I'll have 5 in here, 5 there, and 5 in there. It's split equally between the box and the whiskers. A dot plot is really more of a frequency distribution, just showing you the frequency of values. So I'm going to say a dot plot is frequency of values shown as dots above a number line. A lot of people like this display because you can also see a mode. You can also pretty much make out the median by counting. You're going to have to still calculate the mean if you're going to do it that way. But these are the 3 main ways to look at data. Now let's talk about what I mean by distribution. There are 2 things, or one I'm going to show you at the beginning, the normal versus not normal distribution. It's going to be most easy if you look at pictures. Now I'm not going to talk about these pictures. I've got some other ones that are much cleaner. So I'm going to try to reference all 3 types, a histogram, a box plot, and a dot plot, with the entire rest of the video so you can kind of make sense of it depending on what your display looks like. So these would be examples of a normal distribution. Normal distribution means everything is symmetric. So I'm going to write that word down. Symmetric with respect to the shape. So if I'm looking at bar graphs, we're going to see kind of this general bell-shaped curve. If I'm looking at a box plot, you're going to see that the box and the whiskers are very evenly spread out, very symmetrical on either end, on either side of the median. And then for a dot plot, you're going to also kind of be able to make out that bell-shaped curve. You'll have more dots in the middle, and then they kind of fan out on the sides. That's what a normal distribution would look like for each one of the types. Something that isn't normal, not normal looking, with respect to histograms would be something like these. Notice how these bars are not symmetrical. They kind of bounce up and down. It's tall at the beginning, then dips down, gets tall again like that. This one over here starts kind of low, gets tall towards the end, and then just drops off very quickly. This one would be the flip side of that, tall at the beginning, then kind of fades to the right. That would be an example of not normal distribution for histograms. If we're looking at box plots or dot plots, these would be considered not normal because you see that the box is pushed further to the left, or on this one pushed further to the right. It's not symmetrical, so not normal is going to be referenced as not symmetrical, or I can say asymmetrical, asymmetric in nature, not bell-shaped. Here we see some dot plots that are not bell-shaped. They kind of tail off. This one is kind of all over the place, not normal. So if you're taking notes along with me, I'd like you to write down normal versus not normal. A normal distribution would be something that's symmetrical, symmetric, or symmetrical with respect to the bell curve. I am going to write bell-shaped. Bell-shaped. You'll hear of a normal bell curve. Any data that's displayed like that with this shape is going to be considered normal. So not normal is going to be asymmetrical. Not bell-shaped. Okay, it's going to have a tail on one end or the other, or it's going to be bouncing all around. All right, that's one way we can talk about normal versus not normal distribution. Something else we can talk about is skewness. Well, I'm not even sure if skewness is a word. That's how I talk about it. Skewed data is when the data trails off to one side. So I'm going to write that. When data, in its display now, you have to look at a picture. When the display trails off to one side or the other. We're going to talk about left and right skewness. Let me show you what I'm talking about. Let's look at these images. I've got each type displayed here. I've got histograms at the beginning. I've got dot plots in the middle and box plots in the end. And I want you to make sense of what I'm talking about with respect to the data trailing off one side or the other. On this side, I tried to keep it logical. These would be considered left skewed or skewed left. The data is skewed left. Why? Because it kind of tails. The tail of the data is on the left side. This one on the left side kind of drops off very quickly, but it trails off. I like that word, trails off. When I'm looking at the box plot, I see a large chunk of data. Half the data is right here, kind of pushed to the right. 1/4 of the data is over here. I've got a large chunk of data over here and a smaller, it's spread out, it's smaller over here. Not small values, I'm saying there's fewer data points on the left. So fewer on the left. That's why we're going to say it is skewed left. Flip side of that, these would be considered right skewed or skewed right. The data trails off to the right, trails to the right. We have fewer pieces of data on the right than on the left side. That is with reference to skewness, or when we say skewed data. So I wrote down here, when data trails off to one side or the other, and you have to pay attention. Wherever the tail is what side we'll say it is skewed towards. Something else we can talk about with respect to distribution of data is what we call spread or variance. Kind of just depends on the language your teacher is presenting or is in your textbook or what have you. Range, you're probably very familiar with. Range is the difference between the highest and the lowest number. Difference between the highest and the lowest number. So you're going to think to yourself, whatever the maximum value is minus the minimum value. That will give you what we call the range. If you're asked to find the interquartile range, that's just the difference between the quartiles. The difference between quartiles. You'll take the quartile 3 number and you'll subtract the quartile 1 number. That will give you interquartile range. Something else you can talk about is what is referred to as standard deviation. Standard deviation is just a measure, it's a value that shows how far data is away from the mean. So your data can be really close, clustered towards the mean, all tight, or it can be really spread out, in which case you'll have a larger range value. Let me show you a little bit what I'm talking about with respect to spread or variance. Then I'll speak again about standard deviation. So when we look at these images, do you see how I've got two histograms side by side? I want you to pay attention to something. This histogram has an x-axis that goes from 0 to 10. This x-axis goes from 0 to 10 as well. Notice though that the data is spread, or the range goes from 1 to 10, or I would say the range is 10 minus 1, or 9 units. This has a range of 9. This particular set of data has a range from 3 to 8, or I could say 8 minus 3, a range of 5 units. So because this 5 is less than this 9, we'd say that this data is less spread out versus more spread out. Should be quite simple or obvious visually, but you really need to pay attention if you're comparing two sets, looking at the values, the actual range values. We can look at a dot plot in much the same way. If I have dots that are spread out, you have a larger spread or a larger range versus not as spread out. All right, let me finish with talking a little bit about standard deviation. Standard deviation for some students is scary, and I think it's scary just because the formula to calculate the value for standard deviation is a little tricky and a little, I'll just say complex, okay? But I'm going to show you how to find the standard deviation using your calculator. It'll make it easier to deal with. But you see the bell curve that I have in this picture, this symmetrical shape? What I want you to make sense of with respect to standard deviation is this right here. The middle, the peak of your bell represents your mean value. And I'm going to tell you, if your curve is bell-shaped, all perfectly symmetrical, it probably means that your mean, your median, and your mode are all hovering around the same value. Okay? If you move out away from the mean, now this is what I mean by move away from the mean. This vertical line represents the mean value, whatever it is. If I move out away from that mean in either direction, to the right or to the left, bigger or smaller, I'm going one standard deviation out from the center. When I go one standard deviation out, the idea is that this group encompasses about 65.2% of the data. So 65.2% of the data should be in this space away from whatever the mean value is. If we go a second standard deviation out, so from the mean, if I go out, I'm going to take it down to here. If I go out 2 standard deviations out now, that means one and then another in both directions. What I'm looking at is approximately 95.6% of the data. Okay, so in other words, if I'm going to cover up this data, almost all of the data, 95.6%, is going to be in this space right here. And then we can go still more standard deviations out. I'm going to go one more standard deviation out from the mean. So I'm going to take it all the way from the mean out. So 1 standard deviation, 2 standard deviations, 3 standard deviations out. when I go 3 out from the mean in either direction, now I'm talking about almost all of the data. Statistically speaking, I'm talking about 99.7% of your data. That's almost all of it, so close to 100. So when you're talking about going 3 standard deviations out, you should be including approximately 99.7% of the data. Let me show you examples so you can see what I'm talking about if you are ever asked to find the standard deviation of a set of data. I have an example already drawn out for you. This example represents test scores. It's just a small class. But what I want you to see is I'm displaying it in a dot plot. I thought the dot plot might be the easiest to look at it. When we calculate standard deviation using our calculator, I'm going to go ahead and write down the measures of central tendency as well so you can see something. And the mode. And then I'm going to also write standard deviation. Standard deviation. I'm going to abbreviate just to have space. And I don't know if you noticed, but I was using this symbol right here. That's a Greek letter sigma. It's a lowercase sigma, and that's often used to represent standard deviation. The mean in our calculator is going to be an X with a bar over it. All right, you're looking at these dots. I'm hoping you're looking at these values down here. If you want to consider them percentages, that's fine. But you see the general shape of my dot plot is bell-shaped. It's almost a perfect bell curve. It's not perfect, but it's pretty close. Okay, so let me show you what I'm talking about with respect to using our calculator to calculate the mean, median, mode, and the standard deviation. So I'm going to take my data. You may not be able to see everything I'm pressing just because I want to be able to show you this dot plot along with my calculator screen. All right, here we go. I'm going to enter these pieces of data in my stat function. So I'm pressing stat. I did not press the right value. I just press second quit, just in case you don't know. If you get something in your screen and when you press clear, it doesn't help you, it doesn't get you out, press second mode. Above the word mode, you see quit. Second quit. Okay. I want you to press stat. I'm going to press stat and I'm going to press edit. And then in my first list, I'm going to enter the values for each one of my dots. Ready? I have one dot that's to the left of 65. And by the way, notice that my number line is all single units. So each box, each tick mark represents 1 unit. So that means I have one value at 64. 64, enter. Then I have a value at 68, enter. Then I have 3 values at 72, so I'm going to enter 72 3 times. Think in mode, but then I look over here and I'm like, wait a minute, there are 4 dots there, so I'm going to say the mode is, I'll go ahead and write this in right now. The mode is 76. So 76 4 times. Ready? 1, 2, 3, 4. Then I have 3 80s. 80, 80, 80. I have 2 84s. I have an 88. And over here, a 92. So class did very well. All right, pay attention to this now. I don't have 17 numbers in my list. I have 16 numbers in my list. I can ask my calculator to calculate the mean and the median, and it's also going to give me the standard deviation. Remember, I've shown this in another video, but I'll show you it again. To get those values, to get those statistics for you, you've already entered everything in statistics, stat. Now I'm going to press it again. I'm not using the edit function. That's what I just used to enter my data. Now I'm going to press or arrow over to calc. Since this is just one set of values, one set, one kind of data, it's one variable statistics. Press enter. I put everything in list 1, so that's already my default. I'm just going to press enter 3 times. And look what it shows you. It shows you that the mean is 77.5. 77.5 is my mean. This is a sigma, that's an uppercase sigma. Sigma squared, sigma, that's the sum of the values squared. I'm going to go down to this symbol right here. This is that lowercase sigma I was talking about. That's my standard deviation. 7.05, let's just go 7.1. I'll probably round it off to 7 in just a minute. I'll show you why in just a minute. And then I've got 16 numbers. What is the median number? I'm going to keep scrolling down. If I were making a box and whisker plot out of this, these would be the 5 pieces of data I would use. But what I wanted was the median, 76. Okay, move my calculator out of the way and show you what I'm referencing when I speak about the distribution of this data. So I can see where my mean is. It's 77.5, 76, this would be 77, 77.5 is going to be about right there. Okay, so here represents my mean. This is my mean. All right, the median is 76. The mode is also 76. Now, when your mean, median, and mode hover around the same number, you know that your data is pretty normally distributed. Okay, it'll be that bell-shaped curve. Not always, but usually. All right, standard deviation 7.1. This is what it means. If I were to go approximately 7.1 units away from the mean, now keep in mind, I just said a few minutes ago, I'm probably going to round. I'm just doing that for convenience sake, right? If my mean is 77.5, let's put it right here. Don't have much space. 77.5. That's my mean. If I move 7 units away from 77.5, 1, 2, 3, 4, 5, 6, 7, this dashed line right here, and 1, 2, 3, 4, 5, 6, 7, this dashed line right here, this represents 1 standard deviation out. 1 standard deviation out was 7 units. And so what I'm trying to show you is that if I go 7 units larger than 77.5 and 7 units smaller than 77.5, I am encompassing 68.2% of my data. 68% of the class scored within 7 units of 77.5. Does that make sense? And then if I wanted to go another standard deviation out, I would go 1, 2, 3, 4, 5, 6, 7. Draw a vertical line. 1, 2, 3, 4, 5, 6, 7. Another vertical line. This is supposed to encompass 95.6% of our data. Okay, and really, if you look at all those data points for my students' test scores, doesn't it look like almost the whole class? Well, 95.6% of the data, this is a guideline, this is in general, and this is not exactly 95.6%, but it's close, okay? If you want to calculate it, you can. I'm not going to go there in this video. I have one data point outside of that. So if I were to move, and I don't have any more space, but if I were to move another 7 units out, I would be encompassing, for my data, 100% of it. But remember, when I go another 7 units out, another standard deviation out, I'm encompassing 99.7% of my data. All right, I hope that helps you understand data distribution with respect to one variable statistics.